Let me start with a recap of the previous lecture. We defined the space of local matrices on some metric space S hat, which is actually a metric space S together with some boundary region, which may be empty or may not be on the boundary at all. But last time I suggested to squash this region to a point. It's not necessary for the definition. We can just keep it as a subregion. And the matrix, the space of such matrices is a product of all pairs x, comma y that are adjacent to each other within distance r from each other. And a matrix element A sub x, y belongs to this space. This space itself is the space of linear operators from my to mx. So at each point, there is some finite dimensional space attached, and the matrix elements are themselves operators. This is an example where we have 3 points, 1, 2, and 3. These are elements of R. And I'll use pictures to denote matrices because otherwise it would be too long and maybe less clear. But here we're touching a 4-dimensional Euclidean space to each of those points. These are the basis vectors of that space. Let's enumerate them. 1, 2, 3, 4. 1, 2, 3, 4. These are basis vectors of those spaces M1, M2, M3. I'll write down the matrix element between x equal to 1 and y equal to 2. And if those links come with strength j, then the matrix element is A12, 0, 0, 0, 0, j This is just one matrix element. And I meant to explain this picture because I'll be using such pictures. Next, Anton Kapustin.
What is J also an operator acting on what?
J is a number.
Oh, J is number here.
J is a number here. I would like to answer some questions asked by Anton Kapustin. One question was to clarify the definition of a bulk gap of a matrix. And he said that my definition is very formal and it's not clear what it means physically. It is in fact formal and it doesn't mean anything physical. But we need a definition that works. That's all we need. And let me explain why this definition works.
In this case, S has just R.
Excuse me?
In this case, the space S is just.
Yeah, S is R. And S naught is the empty set.
And it's 4-dimensional.
Yeah. But if we talk about the actual Majorana chain, we would like to continue and say this is point 0 and that is point n, where the dangling Majorana modes are. And we would like to discard them. And to discard them, we should set as is not equal to 0, comma, comma n. Okay, the local, the ball gap is defined like this. We have matrix A, and when we don't have problems with boundary mode, we could simply say that the spectrum of A this is a reasonable condition, but it's not convenient in the sense that if we truncate A, this condition is broken. In my formalism, we have to truncate because I don't want to work with infinite matrices. Even if we have an infinite Majorana chain in mind to do calculations, we'll truncate it. So we cannot truncate A. But if we write the condition in the form minus A squared minus delta squared times identity is positive, and call this matrix X. If X is a positive matrix and we truncate it, truncation means compression using a projection on some region, and it's still positive. So it's safe to truncate this matrix. And that's why I used this definition. Now, we truncate to the region S minus margin, where the margin is a neighborhood of S naught. That's because we want to have all matrix elements of this matrix calculated correctly. If we are close to the margin, the idea is that matrix elements are not reliable. They are a result of truncation, and they can be messy. And when we do this calculation, we get some garbage near the boundary, and we have to remove this garbage by doing this compression or restriction.
The spectra.
Yeah. Yeah, thank you.
Then we also know a margin, so it's not just simply taking a submatrix. You have to also modify the boundary, or just take submatrix.
Well, we first truncate A to the big region, which includes 0 and n. Then we square, and then we remove 0 and n.
Just take submatrix.
Submatrix, yeah. But we cannot stay in the same space. To multiply matrices, we need to go out and in.
Okay, yeah. But the submatrix is the summation of A squared.
Yeah,
Okay.
yeah, because A squared xy is sum over z a xz a zy, and this z may lie in the region where our data is not reliable. So, yeah. This was the first question. The second question was to explain functoriality. This definition for any metric space. I mean, S is a metric space, and S naught is a subspace. And if we consider maps that expand distances by bounded factor, this will be a functor. I mean, we have a category metric spaces. Bounded maps. However, something will break down if we consider general metric spaces, so we should be careful. Namely, I mentioned the locality lemma. The locality lemma says that if we have a region and consider the restriction of the matrix to all smaller disks of radius r, capital R. If the norm of the all restricted matrices is sufficiently small, like X restricted to D is less than A for all D, this implies that the norm of X is at most A times this factor 1 plus R over capital R squared. And this is a geometric factor. The proof of this lemma that I know only works in Euclidean space. However, I expect it to work in the case where on the length scale between the small r and the large r, the volume as a function of radius does not grow too quickly. For example, if we are on a tree and each branch has length L, I mean, the distance between these 2 points is L. If L is greater than capital R, then we should be okay. If L is less than capital R, then this lemma breaks down. And for hyperbolic spaces, it's the same. Okay, now let me continue with new stuff. Last time I mentioned softness as one important condition, and I gave an example of softness, like by extending those spaces, we can wiggle our system a little bit. And I'll give examples of such wiggling today. I'll not repeat the definition because it takes time to elaborate. But one thing I want to say is we can enlarge this space naturally. We cannot enlarge that space naturally. By enlarging, I mean we can consider a direct sequence of spaces corresponding to bigger and bigger spaces mx. And when we extend mx and consider antisymmetric matrices on mx with a gap in the spectrum, it is a natural way to map smaller matrices to larger matrices by adding some standard matrix that also has a gap. And such standard matrix is 0, 1, minus 1, 0. And we add as many matrices like that as we need when expanding. Here, if we try to consider a direct system of such general matrices without antisymmetry condition and without a gap, we wouldn't know how to extend them. Now, the next thing is, suppose we have a family of matrices. Parameterized by X. X is an arbitrary parameter space. It can be a C-doubly complex or whatever. But for simplicity, let it be an interval. And suppose we have different matrices A of T for different T in that interval. And let me represent them by colors. We have a lot of color chalks, and I'll make use of them. Should be used. T equals 0. Let it be white. T equals 1/4 will be yellow. T equals 1/2 will be pink. And T equals 3/4 blue. And T equals 1 green. Now, out of this sequence, we can construct one matrix on a real line. I assume that A of T belongs to local matrices of some interval, like 0, A. And now let's map that interval to the parameter space, which is from 0 to 1. So we map X to T, and write T is A to the -1 times X. And now, instead of having colors as a function of parameter, or a matrix as a function of parameter, we can have this matrix as a function of space. And let me draw it, and then I'll explain what it actually means. So this interval from 0 to A is mapped to the interval from 0 to 1, and we have a matrix that an object that is white in the first quarter, maybe less than a quarter, and then it's yellow, and then it's pink, blue, and green. And make it more visible like this. Okay. So what does it mean? We're constructing a new matrix. A tilde with matrix elements X, Y equal to 1/2. This is to preserve anti-symmetry. conceptually, you can look at just the first term. It will be A of f of x, where f of x is A minus 1 x, and it was denoted by t. Xy plus so the matrix element is evaluated between two nearby points. And since these points are close to each other, almost makes no difference whether we use f of x and f of y. But since we want the matrix to be exactly antisymmetric, I used both. So this is what I call spatial interpolation. And this is an example of a spatial interpolation. Previously, we considered one parameter family of matrices that begin with with this, and that is A of 0. And it goes to this. The Majorana chain. It can be longer. And this is A1 and A of t. And I mentioned that if there's a gap, then this one is also gap because they anti-commute. A of 0 anti-commutes with A1. So this is a one parameter family of gapped matrices. And using spatial interpolation, we can construct a new matrix that on the left looks like this, and on the right looks like that. So it will be something like this comes first, then next we have both things with should say both things with some coefficients, and in the end we'll have the second pattern. And now, ignoring microscopic details, let me draw it this way. Here, there are some details that need to be kept. This coefficient is j, and that coefficient is minus j, to make them anti-commute. So the first line represents A, and the second line represents the complementary object minus A. And they're glued on the left hand. So using special interpolations, we can glue things together. Now, there is a third operation I want to show that follows from the previous ones. It's called folding. So let's consider a one-dimensional matrix A. And let's use this trick to produce a copy of A minus A glued at the ends. Now, we can glue this thing in the middle. And the first thing can be produced out of nothing or out of the trivial matrix that is a bunch of blocks, 0, 1, minus 1, 0. So we can produce this structure. And this structure is the same, exactly the same as the new structure I'll show. Because if we project onto this line, let me make it slightly better by highlighting minus A with yellow, and then the yellow lines are this. It's a double fold. So we can just rearrange those layers in the vertical direction. The vertical direction doesn't mean anything because our actual space is represented by the horizontal direction, and the vertical direction is there to show the direct sum structure. We compose matrices to make a direct sum. So this is a double fold. Somehow it's difficult to produce a single fold, but we can produce double folds out of nothing. Then we can produce any even number of folds by continuously transforming the original matrix A. So we get this matrix. And this is still equal. Now, I should say A is equivalent to that, and maybe here it's inequality, but since we're adding more folds, then it's this equivalence up to continuous paths. And we can further consider inequivalence up by continuous paths where we do change the geometry, not only just draw the picture differently. And the new picture is this. We just rotate each fold and make it vertical. And since those folds consist of actual points, this rotation moves those points. And here I'm using wiggling in addition to the spatial interpolation. The spatial interpolation was used to glue them together, and wiggling, the thing I described last time, is used to make this rotation. And now we have a thing continuously connected to A, A tilde that looks like this. And it's multiple copies of A and minus A.
So what's the difference between the last two pictures?
The last two pictures,
Yeah, the one at the bottom picture.
they're geometrically different because the geometry means projection onto the horizontal coordinate, onto the horizontal axis. And the projection is different. Here, A is longer and minus A is short, and they're all the same length.
So the parameterizing space is constant, not fixed altogether, to be just a real line. Is it correct?
What is fixed?
So parameterizing space is unchanged. Is it correct understanding?
Oh, the parameterizing space has been used and it's gone because we used the parameterizing space to produce gluing. But as a result,
Yeah. Sorry. What I meant was like the
the physical space.
direction. Yes.
Yeah, the physical space is the horizontal line. Yeah.
Could you remind what you mean by wiggling? Do you mean moving the lattice sites around?
Yeah, moving the lattice sites around. Yeah, exactly.
Alexei, one question. You said this vertical direct doesn't mean anything. No, it doesn't. Picture.
Oh, sorry, the sound is bad. I cannot hear.
The last picture, does the vertical direction mean anything?
Yeah, exactly. The vertical direction doesn't mean anything.
But it's just a longer line.
Well, we can draw those points, and there are some couplings between those points. Near the ends, these points are coupled, and in the middle, they are not coupled. And we're projecting all those points to the horizontal line, and we get some couplings.
Like a Heidelberg swindle.
Yeah. But it's not a swindle. It's actually.
It's not.
Yeah, right. How is it useful? We can start with A having some locality radius R. And we produce this A tilde that may have a similar locality radius. And in the process, we use this path that actually makes the locality worse, like 2R. To make these rotations, we may move points by distance greater than R. But having arrived at this picture, we can improve the locality. We can start stretching those things in the vertical direction, which doesn't mean anything, and add more and more points. And in the horizontal direction, it will become more and more local. And I call this an improvement map. And Michael Friedman used this improvement map in a slightly different setting for quantum cellular automata, which are local automorphisms of operator algebras. And the same trick works in many cases. So the point of this trick is to improve locality. Remember that we can improve the energy gap at the cost of locality. Things become non-local. But we can also improve locality using the folding trick. And this way, basically, everything becomes as local as we want, although not absolutely local. And now,
So the cardinality of the lattice, that it really increases when you do the folding thing.
exactly. Now let me formulate what should we do to define nice spaces of local matrices? We have spaces with a bunch of parameters, and we would like to get rid of them and get a single space for each n, for two-dimensional matrices, three-dimensional matrices, and so on. So we want to do this first. As head, we skip M, and the locality radius R, and delta will be here, and these are intersymmetric matrices. These are the union over all M's, which are embedded into one another. It's basically a direct limit of
For the Boolean trick, are you supposed to apply this to one dimension or other dimension?
you can fold in one direction, then you can fold in another direction. And in n dimensions, you need to apply it n times. No. This is done for Rn. Or for a ball relative its boundary. Yeah, basically, it's done for Rn. So this is the union of spaces where we can add as much wiggling space as we want by increasing M. Then we would like to define and this is an inverse limit. Yeah. Here there is a question mark because for each particular choice of Rn delta, those spaces are quite irregular. When we take the limit, for example, when we take delta to 1, the space of matrices shrinks. And imagine that we have space with some topology, like we have land and sea, and we're interested in the shape of the land. And the land can be an island which has mountains, and there is some little island that is almost underwater. Then the sea level rises, and this island disappears. But there might be another island that will occur. So the new shape can be this one. And each time there will be some spurious pieces, and we would like to get rid of them. We would like to consider kind of persistent topology of that shape. I have not figured the exact details how to define the persistent topology, but Mike Hopkins taught me about pro objects, and there is a definition in terms of pro objects. It goes roughly like this. We don't actually define this space directly, but rather we define first the space of maps from X, any base pointed CW complex to this guy. And then we would like to take a limit of this set of sets. For each R and delta, it's a set. And we would like to take a limit. And in the end, we would show that this limit gives a representable functor, and we'll recover the space that we need. I don't want to actually take a limit. I want to take a limit without taking a limit. And here I consider this space as a function of R and delta is an inverse system, and take it as an object. And one can define morphisms between such objects. And we need to show that these objects are representable by a functor that satisfies the Meyer-Vietoris axiom. And then we can apply the Brown representability theorem. And to show that this functor satisfies the right conditions, we will use the folding because it provides an improvement. And it basically the idea is we get these spurious islands because we consider paths for the same sea level as we defined the islands themselves. But we could instead consider paths like between these two purple islands that go in a bigger region for different values of parameters. And this path exists because previously in this, when the sea level was lower, those islands were connected. And we take them as the same connected component. And due to this trick, no limit is actually necessary. And we can extract this persistent homotopy type. Okay, so if you believe me, just let me proceed. Now I'll assume that there is a unique space Ln that doesn't have any messy parameters. And I want to show that such spaces for different n form an omega spectrum. So let me define two maps. And those maps are mutual inverses up to homotopy. So how do we construct alpha? And we want to construct alpha n, but I'll show some pictures for alpha 0. And the picture will be similar to this folding thing, but the vertical direction will be interpreted as a parameter rather than some dummy variable. So we first consider a path from A0 plus minus A0. A0 is a trivial matrix. And that is connected to A plus minus A. There is a path. And that path is given by A of T. And now I will use this path to construct alpha 0 of A. That is an element the new variable that is related to the previous T. So let me draw this new variable vertically. This is T, and it will go from 0 to 1. Maybe I should call it T tilde to distinguish it from the previous T. And initially, when T tilde is 0, we'll have an alternating sequence of A0 actually, minus A0. And I'll draw them as dots and empty dots. And it can be a long sequence. During the first time period from 0 to 1/2, we take this pair of matrices A0 minus A0 and morph their sum into A and minus A. So at some intermediate times, they're coupled, but at T tilde equal to 1/2, they're decoupled. And then we go back to A0 and minus A0, but we do it in alternating order. So we get okay. And this is similar to transporting system A from the right to the left. As a result of this picture, a copy of A, notice that this remains unpaired. So this is still A. And this is minus. And there is a similar story about transporting electric charge faster than light. It can be done if we arrange something on the path between two locations. We create a bunch of electron-positron pairs and then annihilate them in alternating order. So this way, we produce a pair of A and minus A. And one can also say that we have pushed or pumped A from the right to the left. And A can be n-dimensional, say two-dimensional, and there is a pump that moves two-dimensional objects through three-dimensional space. now, what is beta zero? Beta zero is a spatial interpolation. If there is some a tilde that is an element of omega of L1, what do? We say that a double tilde of x, y equals roughly a tilde of x plus some other thing for anti-symmetrization. So it's the spatial interpolation that was used previously. And the spatial interpolation corresponds to cutting this picture diagonally, because t tilde becomes a function of x. And what do we get on the diagonal? On that diagonal, we have some dimers that correspond to a transition from A0 to A. So there are some dimers. And on the right, we have dimers corresponding to the opposite transition, because the right end corresponds to t tilde greater than 1/2. So now we have dimer like this, and maybe a dimer like this again. And in the middle, we have maybe one, maybe three, but an even number of things that look like A and minus A. Let me put three of them. And let's pick one, because there is always an even number. And we can now push all this back in time to t equals to 0, and all those forward in time to t equals to 1. And in the end, those dimers will disappear. And this is done by a continuous transition. And the thing in the middle will remain. Now, there is one subtlety. This picture by itself represents a one-dimensional object, a local matrix in one dimension. However, this local matrix can be cut because it's not relative boundary. And it's not relative boundary because we consider a loop. And by definition, a loop begins and ends at the distinguished point. And that distinguished point corresponds to just disjoint copies of 0, 1, minus 1, 0. That's what why we can cut this thing anywhere. We can cut it here, for example, and consider all of this stuff as a zero-dimensional object. It wouldn't be possible if the path started at a non-trivial point where the cut would produce some garbage at the ends. So it's indeed a map. Beta 0 is a map from the loop space to the space of matrices in one dimension lower. And this argument shows that beta alpha is homotopic to the identity map. And one can also show that alpha beta is homotopic to the identity map on the loop space. That is slightly more complex, and it involves folding explicitly. Here, I didn't use folding. This picture just looks similar to folding, but it's in the parameter space rather than in time. And the proof of that uses folding explicitly. Now, I have defined an omega spectrum of local matrices. And these arguments were completely general. Basically, anything that is invertible, local, and soft makes an omega spectrum. That's it. And I haven't used any details except for justifying those properties, invertible, local, and soft. The same argument can be applied to interacting Hamiltonians, say fermionic Hamiltonians with quartic terms, like products of four Majoranas. One needs to define invertibility, and one needs to care about softness. And these are some non-trivial analytic details I'll try to address tomorrow. The same thing should be applicable to quantum cellular automata, local automorphisms of operator algebras. But there is some problem with softness that people have not studied. We need to do this spatial interpolation to ensure softness. And spatial interpolation probably requires considering approximate automorphisms. And yeah.
Didn't want to stop you from what you're saying about it.
No, yeah, please ask. Yeah.
You allow quartic terms, then do all these moves, like not swindle move, do all these stay in the realm of quartic?
No, there will be 6 order terms and so on. Yeah, we approach it differently.
You can make it work for quartic.
I haven't tried. I haven't tried to restrict myself to quartic terms. If I allow quartic terms, I'll allow everything.
Allow it. Okay. I guess I think I misunderstood what you said.
Yeah, I mean, there is a qualitative difference between quadratic and anything higher than that.
Okay. Oh, so quartic just meant two.
Yeah,
Okay.
yeah. But since this argument is completely general, it doesn't give any hint how what the spectrum actually is. And the calculation of the spectrum has to do with Bott periodicity. We need some extra structure. And that extra structure is, we consider not just local matrices, but local matrices with Clifford symmetries. We define local matrices, they anti-commute with some other Clifford algebra that has nothing to do with Majorana fermions. And using that extra structure, we can decompose the map alpha like this up to homotopy. There are spaces Ln with E positive Clifford generators and Q negative Clifford generators. And we can map that to Ln plus 1 with P minus 1 positive Clifford generators and Q negative Clifford generators. And when we consider positive and negative Clifford generators, it only depends on P minus Q mod 8 due to Bott periodicity. The Bott periodicity is easy to prove for Clifford algebras, and here we're proving the topological Bott periodicity. So there is this map, let me call it mu, and there is another map, nu, which is a standard map in case theory. It's described in Ruby's book, for example. It goes to omega of Ln plus 1. Here, the dimensionality doesn't change. The nature of local matrices doesn't change. PQ. And the composition of these two maps is equivalent to alpha up to homotopy. So one needs to construct those maps explicitly, and this is very simple. Unfortunately, I've run out of time. I cannot show it today, but I can describe both maps explicitly, and especially useful is the second map when it's combined with beta. This way, we can start with an n+1 dimensional system and get an n-dimensional system with an additional positive Clifford symmetry. And by iterating, we can start with any n-dimensional system and produce an equivalent zero-dimensional system. And then use some linear algebra package and decide which phase this system belongs to. So there is an algorithm that takes a finite patch, and maybe I'll take 10 minutes from the next lecture to describe that algorithm. It spits out a topological invariant. Okay, thank you for your attention. Yeah, please.
About that feature, so we'll make that cut, the pink line.
Yeah.
It seems that there is a dangling minus a on the right hand.
There is a dangling minus a.
Top right corner, but it's not there in the picture.
Right, but now Ln+1, in this case L1, is relative to boundary. So we're free to discard anything at the boundary. Yeah, you're absolutely right. If we keep this dangling A, it won't be good, but we're allowed to discard it. So we just I cut like this, but there are some dangling things on the ends, which we discard.
So when you say this constructive loop, it's also in the sense of with respect to the boundary.
Yeah. L1 by definition is relative to boundary. Yeah.
So this limit you wrote, if this space S is not, or D is not something with boundary, but a close compact Hamiltonian map, would this limit actually stabilize when R is smaller than some number with the radius?
Yeah, it stabilizes. Yeah.
It stabilizes.
Yeah, it stabilizes.
So why do you want to work with something with boundary rather than just do it on a compact space? I mean, closed compact space.
Well, like a sphere, for example.
Yeah, like a sphere.
Well, this relative setting gives some flexibility. If I work on a compact space, I will get additional topological invariants that I don't want. They will complicate the picture. For example, on a sphere, there is an invariant that gives the total fermionic parity of the whole system. Like the sign of the Pfaffian of matrix A.
But you still want to take thermodynamic limit substance. You still want to
Yeah.
want it to belong to having to start with.
Yeah. You can do it with an infinite lattice, but I actually like it to do a relative boundary. Just an algorithmic way to do everything, well controlled.
Say that what you're telling us here is that you completed your program, or is there a lot left?
It's the beginning.
This way, solving these limit questions, of course, I could calculate the spectrum. It happens to be the KO spectrum, shifted in dimension. And that would be a very boring answer because people know the KO theory. And the actual problem is to compute the spectrum for a different type of local object, so a different type of material. And there are variants. I believe that invertible phases, invertible states are easy to deal with the quantum cellular automata, but quantum cellular automata is yet another example we could try to study. But to study them, first we need to justify locality, and I'll talk about that on the next lecture. So we need to justify, in particular, softness for quantum states. The softness follows from adiabatic deformation, quasi-adiabatic deformation, the trick invented by Hastings. And for quantum cellular automata, it's still open. But again, this is just a little going further. The ultimate question is to calculate the spectrum. And on the next lecture, I'll explain why it is difficult and what's missing.
Algorithm that you will describe applies to quadratic.
Yeah, exactly.